Good evening. Today we are going to discuss about the gating design. So here we are going to make the design of the gating system. The channel through which the molten metal is going to flow in the mold cavity, that sections we are going to design. Design in the sense it is not merely drawing. We are going to give appropriate dimensions in the design. Okay, so that is what we are going to do. But here coming to this point, the gating system design is done by using two basic principles of fluid mechanics. One is Bernoulli's theorem and another one is law of continuity. So here the Bernoulli's theorem states that the energy head is going to remain constant at any section in the mold cavity with respect to the mold I am talking about. So it is going to remain constant. So mathematically it is generally denoted by H plus P by W plus V square by 2G is equal to constant. Whereas the law of continuity states that the flow of metal or the rate of discharge is going to remain constant at any given cross section in the mold cavity. Understand this, the molten metal acts as a fluid. That is why the laws of fluid mechanics holds good for this molten metal. Okay, here H is the potential head, P is the pressure, W is the specific weight, and V is the velocity of the molten metal inside the mold cavity, and G is the acceleration due to gravity. In this second part, that is law of continuity, we have A1 V1 is equal to A2 V2. A1 is the cross-sectional area of that particular section. Maybe it is a runner or it may be a sprue or the ingot. So at any given cross-section, the discharge or the mass flow rate is going to remain constant. That is what this law of continuity states. And its unit is what? Its unit is meter cube per second. Okay, so A is the cross sectional area, it will be in terms of meters, V will be velocity, it will be in terms of meters per second. Okay, so this is how we generally use this gating system design. Always remember that the pouring time is calculated first. With the help of that we are going to calculate pouring rate, and after calculating pouring rate we are going to design all the other parts of the gating system using this equation. There are two basic things that comes into picture in designing the gating system. One is the law of continuity as well as the Bernoulli's theorem, and another part is the Chevron's rule, which is going to tell us about the cooling time. Okay, so with the help of all these things we generally make the design of the gating system. Now let us see first the pouring time, how we calculate pouring time. Pouring time. So this is a typical sand mold. This is the ladle. Okay, this is the pouring basin. And this is the molten metal over here. And okay, so here basically we are going to pour the molten metal inside the mold cavity. As I explained in the earlier classes, we are going to melt the metal in the furnace, and after that we are going to take the molten metal from the furnace with the help of something called as a ladle. Okay, and from the ladle we generally take this molten metal to the pouring station, where the prepared sand mold will be there, that is the assembled cope and drag part of the sand mold will be there, and the spot of the ladle is directed towards the pouring basin. Okay, the person who is going to pour it makes sure before pouring that the temperature of the molten metal should be more than that of the melting point of that particular metal. Okay, generally we keep 100 to 150 degrees Celsius access to that of the melting point. So if it comes below 50, that is if say melting point is 1400 degree, and while pouring if it is 1450, then we stop pouring there itself. Okay, because there are certain drawbacks, you know, in between if it gets freezed, or in between if it solidifies once it loses its temperature below the melting point, then at that time the flow of the metal will not take place, and it is going to restrict the movement. Okay, and it is going to cause a defects. For that reason, generally what we do is we are going to pour the molten metal considering the temperature to be on the higher side. Okay, so that is done, and here the time required to pour, for example, to pour this particular cavity, how much time is required, that is calculated. If we pour it at a very fast rate, then what is going to happen is the flow of the fluid inside this is going to be turbulent like this, and subsequently it is going to damage the parts or the walls of this molds. Okay, mold cavity as well as the gating system, those parts gets damaged because of the turbulent flow. As I explained in the last class, the flow has to be laminar as possible, otherwise the turbulence has to be reduced. Okay, so thus the pouring time should not be too less. What happens if pouring time is too more? The temperature of the molten metal required will be very high if you are going to pour very slowly. Okay, for example, the molten metal whatever we are going to pour, if it is nearby to the boundary side and we are pouring it slowly, then there will be a fast cooling that is going to take place, and subsequently the temperature will come down and there will not be any progressive flow of the molten metal. So that will take place. So for that reason, it is always seen that the pouring time has to be the optimum. It should not be neither too more nor too less. It should be the best time. Okay, within that stipulated time, we are going to pour the molten metal such that it will fill the entire mold cavity. Okay, so there are different formulas for different metals. Now we are going to see for only two different types of metal, grey cast iron and steel, and according to the weight, again grey cast iron is classified into below 450 kgs and above 450 kgs weight. For that we have two different formulas. Okay, so based on that we are going to solve certain numericals. So pouring time T for grey cast iron, below 450 kgs, pouring time T is equal to K into the bracket 1.41 plus T divided by 14.59 whole multiplied by square root of W these many seconds, and above 450 kgs T is equal to K into 1.236 plus T divided by 16.65 multiplied by cube root of W. Okay, where W is the weight of the casting, K is a constant, and it is generally given by fluidity of iron in inches divided by 40. Capital T is the average section thickness in millimeters, and for steel T is equal to 2.4335 minus 0.3953 log W into square root of W, this many seconds. Here again W is the weight of the casting. Okay, as I explained in the earlier classes, metals will be having their own composition, and generally steel and iron differs in the amount of carbon content. So here, depending upon the carbon content, there will be different allowances we provide. Okay, generally steel shrinks more, whereas cast iron, it tries to expand when it solidifies. Okay, because carbon will transform into graphite. Okay, so this is the reason why the risers are generally not provided in simple castings of cast iron, or sometimes whatever risers we are going to make use of will be having a dimension smaller as compared to the steel castings. Steel castings, in extreme cases, we have a casting whose riser will be having the width approximately equal to the width of the casting. Okay, so this is the thing with different metals. So these are the formulas we make use of. For grey cast iron below 450 kg, we have the pouring time T is equal to K into 1.41 plus T divided by 14.59 whole multiplied by square root of W. W is the weight of the casting, T is the average thickness. Okay, and K is calculated by fluidity of the iron in inches divided by 40. Above 450 kgs, T is equal to K into the bracket 1.236 plus T divided by 16.65 into cube root of W, where again W is the weight of the casting, K is the fluidity of the iron in inches divided by 40. Then we have the pouring time for steel, that is given by 2.4335 minus 0.3953 log of weight of casting. The entire thing is multiplied by the square root of weight of casting. Now we are going to solve a simple problem on this particular formula. Simple numericals we will solve on this. Calculate the optimum pouring time pouring time for a casting whose mass is 20 kgs and having an average section thickness of 15 millimeters. The materials of the casting are are grey cast iron and steel. Consider or assume fluidity of iron as 28 inches. Okay. Now we will first solve for grey cast iron solution. First one is grey cast iron. So T is given as 15 millimeter. Weight of the casting is 20 kg, that is W. 20 kg. K we need to find out, 28 divided by 40. So we are going to just keep it as it is and substitute in the formula. We know that pouring time for cast iron below 450 kg is equal to K into 1.41 plus T divided by 14.59 whole multiplied by W. So K is 28 divided by 40 and this is 1.41 plus 15 divided by 14.59 into square root of 20. So we are going to get approximately 7.632 seconds. B. Steel. Okay. For steel, we know that pouring time T is equal to 2.4335 minus 0.3953 log of casting weight into multiplied by square of casting weight in terms of seconds. So write this as it is, 2.4335 minus 0.3953 into log of 20 the square root of. So this is going to be 8.5825 seconds. Okay, so I'll explain this once again. In the problem, the average section thickness is given as 15 millimeter, that is this particular part. Casting weight is given as 20 kgs, this particular part. Okay, and they have told us to find out the pouring time for two metals. One is grey cast iron, another one is steel. The fluidity for the grey cast iron is given as 28 inches. Okay, First note down the given data, and then for grey cast iron we know the pouring time T is equal to K into the bracket 1.41 plus T divided by 14.59 whole multiplied by the square root of weight of casting. So here in this formula I have substituted the values of K. K value is 28 divided by 40. Okay, so this is what we have substituted. Then 1.41 as it is, T average section thickness is given as 15 millimeters. So that we have substituted, divided by 14.59, and the whole thing is multiplied by square root of 20. That is what we are going to get it as 7.632 seconds. Okay. Similarly, for steel, we have the formula for pouring time. T is equal to 2.4335 minus 0.3953 log W. The entire thing is multiplied by square root of weight of casting. So here, wherever the weight of casting is there, we are going to substitute the value of weight, that is 20 kgs. So once we are going to substitute those values, here we are going to get 8.58253 seconds. Okay, so this is how we find the pouring time. Next one is choke area. Next one is choke area. So H is this effective screw height. I'll explain this. For top gate, H is equal to small h, that is height of screw. For bottom gate, H is equal to H minus C by 2, where again H is height of screw and C is total height of mold cavity. The last one, for parting gate, we have H is equal to H minus P square divided by 2 times the C. Okay. P is the height of the mold cavity in cope. Apart from that, W is the weight of the casting weight in kg. is the choke area in mm square. T is the pouring time, small t, it is the pouring time in seconds. D is the mass density of molten metal in kg per mm cube. G is the gravity in terms of meters per second square. C over here is efficiency factor, and H is the effective metal head. Metal head. Okay. In the last class, at the beginning of this particular unit, we have discussed about the gating system, and there I have explained something called as a choke. Okay. So here, how to find the area of the choke? What is this choke exactly? Let us understand first. In order to regulate the velocity of the molten metal, which is coming from pouring basin to the sprue, then it has to move to the runner, and from there it is going to the mold cavity. The velocity of this molten metal has to be regulated, and this is what is being done by using a particular small part in the runner called as choke. So how to find the area of the choke? So area of the choke is found out by using this equation. A stands for area of the choke in mm square is equal to W, that is weight of the casting, okay, in terms of kgs, divided by density of the molten metal. See, the density of the solidified metal and density of the molten metal are different. They are not same. Just keep this in mind. Okay, while solving the numerical, we'll come across this type of problem. So here G is the gravitational force, and it is in terms of meters per second square. We generally consider it to be 9.18. C is the efficiency factor, and H is the effective metal head. Generally, that equation is derived by Bernoulli's theorem. So this effective head H is different for different types of gating system. As I explained in the last class, in top gate, directly the metal is going to be poured inside the mold cavity with the help of a vertical sprue that is going to directly attach to the top face of the casting or mold cavity. So there, how we are going to find this effective metal head is H is equal to small h, that is height of the sprue, okay, through where the metal is coming. For bottom gate, that is the gating system where the runners and other parts of the gating system are situated below the parting line, those are called as bottom gate, and here H, that is effective metal head, will be equal to H minus C by 2. Okay, what is C over here? C is total height of the mold cavity. Then for parting line gating system, that is the gating system where exactly the runners and the gates and in-gates are going to fall at the parting line, the separation between the cope and drag, that is what we call it as parting line. And for such type of gating system, we have this equation. So the effective metal head H is equal to H minus P square by 2. Again, H is the height of the sprue and P is the height of the mold cavity only in cope part. Okay, because sprue base is going to come under drag part, so that is not considered over here. That divided by 2 into C. So this equation we make use for calculating the choke area. Okay, in order to maintain the pouring time, whatever pouring time we have calculated, if at all we want to maintain that pouring time, or if we want to stick on to that pouring time, then choke has to be designed properly, because this is the part which is going to regulate or restrict the velocity of the molten metal. The metered quantity of the molten metal is made to flow inside the mold cavity by using this particular part called as choke. Okay. Now we'll solve a numerical on this, and you will understand how to do the calculations or how to make the design of this. For the casting shown in figure, for the casting shown in figure, which is to be made by using grey cast iron, calculate the choke area assume composition factor as 4, pouring temperature as 1300 degrees Celsius, the fluidity is 22 inches, cope height 100 mm, is 100 millimeters, C 0.73, that is efficiency factor, and density of liquid metal is 6.90 into 10 to the power minus 6 kg per millimeter cube. So this is the casting. So we have 4 runners over here. First runner. Then we have second runner. We have third. And fourth. So this is the dimension of the casting, 250 by 50 by 100. Sorry, 500. Okay. As a part of solution, first we will find the volume of this particular casting. Volume of casting is equal to 500 into 250 into 50. That is 6.25 into 10 raised to 6 mm cube. Then weight of the casting is equal to volume into density in its solid form, solid state. That is 6.25 into 10 raised to 6 multiplied by 7.8, 6 into 10 raised to minus 6. That is 49.125 kg. Density in terms of kg per mm cube. Then pouring time T is equal to K divided by 40 to 1.416, 1.41 will take, plus T divided by 14.59 square root of W. Plus 22 divided by 40, 1.41 plus 50 divided by 14.59 into the weight 49.125. So that we get nearly 19 seconds. Okay. Then we have choke area. A is equal to W divided by DT C into square root of 2GH. Okay. So here H is the effective screw height. So here screw base is not visible, so directly this height is taken. This height is also given as 100. Okay. So here W, weight of the casting, it is known, it is what we calculated, 49.125 kg divided by the molten metal density, that is 6.9 into 10 raised to minus 6, 6.9 into 10 raised to minus 6 into pouring time is 19 seconds into C, efficiency factor, that is 0.73. Whole thing is multiplied by 2 into 9,800 millimeters per second square into 100. So it will come out to be 366.648 mm square. There are four ingots. This can be seen from figure. So we consider it to be 367 divided by 4. Sorry, 367 mm square. So area of each ingot can be considered as 361 divided by 4, that is nearly 90 mm square. Assuming cross section as rectangular, the dimensions will be 15 by 6 mm, because width is equal to 2.5 times the height. So here in this problem, the sketch is given for the casting. So this is the casting which has the dimensions of 500 millimeter by 50 millimeter by 250 millimeter. We have a sprue and its effective height is 100 mm. Then we have 4 gates. Okay. So based on this, we are going to design the choke as well as ingots. So design in the sense we are going to find the dimensions and the geometry. Okay. So design is not the drawing. Design is where we are going to find out the dimensions as well as geometry. So here in the question they have mentioned that the metal is grey cast iron. So this particular part of the statement is used for calculating the pouring time. So this will make us certain about what type of formula needs to be used. Okay, and then we have pouring temperature that is given as 1300 degrees Celsius, as well as fluidity is given as 22 inches. Fluidity is used in order to find the pouring time. Again, prior to that, we need to find out the weight of the casting. As I mentioned, the weight of the casting in its solid state will be having a different density. The metal will be having a different density when it is in the solid state as compared to its liquid state. The density will be slightly on the larger side when material will be in the solid state. Okay. So here, whatever the density they have mentioned in the question is of liquid metal, not the solid metal. Regarding solid metal, in the last class we have discussed for the grey cast iron, it will ranges from 7.3 to 7.8, and for steel it will be 8.05, and for aluminum it will be 2.7 grams per centimeter cube. This is what we have discussed in the yesterday's class. So with the help of the same basics, we are going to find out the volume of casting. Volume of casting is 500 by 50 by 250, and we are going to get this much as the volume. When we multiply volume with density, we are going to get weight of the casting. As the metal here in the casting is in the solid state, we are going to consider the solid metal density. So solid metal density is 7.86 into the power 10 raised to minus 6 kg per mm cube. Okay. So grams per centimeter cube is converted into grams per millimeter cube. So that is why we have got this 10 to the power of minus 6. So once we do that, we are going to get weight of the casting as 49.125 kgs. So this casting weight will be substituted in the pouring time formula. So here pouring time, as the weight of the cast is less than 450 kgs, we are going to make use of this formula, K divided by 40 multiplied by 1.41 plus T, that is average section thickness, divided by 14.59. The whole thing is multiplied by square root of W, where W is the weight of the casting, that is less than 450 kgs. So these values we are going to substitute. T is given as 50, so that we are substituting, and then the value of W, that is 49.125. So this we are going to get it as 19 seconds. Once we get the pouring time, we are going to substitute these values in the choke area formula. Choke area A is equal to W divided by dTc into square root of 2gh. Okay. D is the molten metal density, W is the weight of the casting, T is the time required for pouring the molten metal, C is the efficiency factor that is given in the question, and square root of 2g into h, effective height. So here the sprue base is not visible, so that is why whatever the dimension is given, we consider it to be the effective height of the sprue. Okay. So here those values will be substituted. You can see here again the gravity is converted in terms of the in terms of millimeter per second, and because of that we are going to get the values. Okay. Once that is done, we are going to substitute the values and we get it as 367 mm square. Okay. So once we found out this value, as there are 4 ingots, so here you can see 1, 2, 3, 4. 4 ingots are there. So because of that reason, we are dividing this particular total choke area divided by 4. So it will be 90 mm square. So the area of cross section of each ingot is 90 mm square. Okay. But we have one more ratio which we have discussed in the earlier classes, that W is equal to width is equal to 2.5 times height. Because of this, whatever we have calculated is 15 by 6. 15 mm is the width and 6 mm is the height of this particular ingots or entire gating system. Okay, this is how we design the gating system. I hope everything is clear. The most important thing in solving such problems is the units. If units are given in millimeters for the casting, then convert all the other constants or all the other values in terms of millimeters only. Kgs, grams, those unit conversion is very important. Okay. So if unit goes wrong, then completely whatever values you get will be wrong. So please concentrate on the units. Next one is riser design. Riser design. In this we have two methods, one is Keynes method and another one is modulus method. First we are going to study about Keynes method. Here we are going to find something called as freezing ratio. This method is entirely dependent upon surface area divided by volume of the casting as well as riser. We call it as cooling characteristic. So surface area divided by volume of casting, surface area divided by volume of riser, and it is denoted by x. Then we have Keynes relationship. X is equal to A divided by Y minus B plus C, where Y is the riser volume divided by casting volume. A, B and C are constants. Okay. So here in Keynes method, we are going to make use of a word called as cooling characteristic. The ratio of surface area to the volume of casting or a riser is generally termed as cooling characteristic. The inverse of this cooling characteristic is termed as modulus, which is the next type of riser design. In most of the cases, we are going to have the riser which is having cylindrical in shape. Okay, so here this entire thing is derived by a formula or a rule called as Chevronnet's rule. By Chevronnet's rule, we are going to find out the solidification time, and with the help of this, we are going to derive all these particular aspects. So in general, freezing ratio X is given by surface area to the volume, that is cooling characteristic of the casting divided by cooling characteristics of the riser. Okay, so here Keynes relationship with respect to X, that is the freezing ratio, is X is equal to A plus Y minus B plus C, that is A divided by Y minus B plus C. A, B, C are the constants and Y is the ratio of the riser volume to the casting volume. Okay, we'll solve one problem on those riser design. In the last class, we have discussed the functions of the riser or the requirements of the riser, types of riser and the definitions of riser. So, I am directly going for the riser design. So, calculate the size of cylindrical riser height is equal to diameter necessary to feed a steel slab of 25 millimeters by 25 millimeters by 5 centimeters, sorry, 25 centimeter by 25 centimeter by 5 centimeter with top riser assume C is equal to 1, A is equal to 0.1, B is equal to 0.003, sorry, 0.03, solution. Volume of casting, that is 25 by 25 by 5, that is given there. So in general, this is the casting, steel casting, 25, 25, 5, and we have a riser. This is diameter, this is H, and H is equal to D. Okay, so this is 1750 centimeter square. Sorry, it is 3125 centimeter square. Then the next one, surface area of casting is 2 times 25 by 25 plus 4 times 25 by 5. I'll explain this. 1750 centimeter square. Riser volume of riser pi by 4 d square into h, but h is equal to d, so it is pi by 4 d cube, because h is equal to d. That is given, because h is equal to d, that is given. Surface area of the riser is pi d square plus pi by 4 d square. Okay, actually this is pi d into h. This is pi by 4 d square. That is pi into d square plus pi by 4 d square. So in totality we get it as 1.25 d square. So x freezing ratio is equal to surface area by volume of casting divided by surface area divided by volume of riser. So this is 3125 divided by 1750 1750 divided by 3125, and here we have 1.25 pi d square divided by 0.25 pi d cube. So we get it as 0.112 d. Y is equal to volume of riser divided by volume of casting.